During my medical studies, I got fascinated by how many subsystems in the human body cooperate in an elegant, perfect, and efficient way. However, I had the impression, well, I do not really have the methods to really deeply understand what's going on. And that's why after medicine, I studied maths and physics. I got intrigued by self-organization theory. Self-organization theories allows you to explain how complex, very complex systems consisting of many, many, many subsystems generate order, beautiful order, like, for example, these stripes. Very simple mechanisms, nonetheless beautiful, large-scale, coherent order, these clouds, or for example, these beautiful spirals and this chemical reaction in the Petri dish. And a standard self-organization issue or problem is synchronization, being in harmony, doing everything together. In the brain, synchronization plays a huge role, but it depends on the dose of the synchronization. Too much of it massively impairs brain functioning, simply because different neurons have to process different types of information, but if everybody does the same thing, that's not good, and this can cause massive impairment. A general or key example is Parkinson's disease, a disorder about 1 million Americans suffer from. And you know the main symptoms of Parkinson's are stiffness, then slowness of gait, slowness of movements in general, small steps, and tremor. Not all patients do have tremor. And I show you an example of a patient. He was diagnosed in 2007, and this is in 2018. The patient is instructed to simply enter the room, and whenever Parkinson patients have to enter a room, change velocity, change direction of motion, it's difficult for them. The patient had to use a cane, was supposed to use a wheelchair, and had to take about 20 to 25 dopa pills and all sorts of other meds, Parkinson's meds, and nevertheless it had to take them very frequently, but nevertheless was about 50% of the day lying in bed simply because he was so stiff and couldn't move. Now, already in the 19th century, Charcot, a famous, brilliant neurologist in France, observed that his patients who came by train or carriage, they were a bit better. That's why he designed this vibratory chair, for example, powered by steam, natural gas, and it basically simulated a train ride, the shaking vibrations of a train ride or a carriage ride, and the patient had some benefits. So the stiffness decreased a bit, sleep got a bit better. Now, and how is our approach? How does it look like? Well, this is how self-organization comes into play. Already very simple neuronal networks. The red balls are neurons. With plastic connections, can be in very different, very, very different, qualitatively different states. They can be strongly connected, strongly synchronized, everybody's firing more or less at the same time, but they can also be weakly coupled, desynchronized. And the magic about our approach, in all modesty, is that by means of maths and physics, we were able to design stimulation techniques that allow us to move systems from this pathological synchronized state to better states, more physiological, to desynchronized states. And that's the important point. So desynchronizing stimulation enables us to make networks unlearn their abnormal connectivity and hence make them unlearn to produce abnormal neuronal synchrony. That's the core of what we're doing. Now, how does it look like for Parkinson's? We do not stimulate the whole body. We stimulate strategically favorable places, a small part of the skin surface, the fingertips. And why the fingertips? The fingertips have a huge cortical representation. So the part, what you see on the screen is the sensory cortex, and the fingertips have a huge part relative compared to, for example, the legs or the forearm. So in other words, if we stimulate the fingertips, although it's a tiny part of the surface, we already reach quite some volume in the brain, and we know from many computational studies, theoretical studies, preclinical studies, and other clinical studies that desynchronizing effects propagate. And in order to deliver these stimuli, we've designed this glove system. So these are gloves. That's the controller. We're a bit old-fashioned, we have wires. And these tactors, so each of the 4 fingers have a tactor, mechanical stimulate, and the really important, the core point is the stimulation pattern. So this stimulation pattern is called coordinated reset, and coordinated reset means that if you have a large neural population, you do not stimulate everybody at the same time. What you do is you stimulate at different sites at different times, weekly. These are weak vibratory bursts, no strong stimuli. It actually doesn't really work well with strong stimuli. We have to stimulate in a gentle way. And in this way, we disrupt synchrony and cause the therapeutic effects. So let's get back to this gentleman I've shown you at the beginning. So he came to us in August 2018. And as I said, he took between 20 to 25 dopa pills, another couple of other meds. And from day 1 on, he dropped down to 6. There was no instruction to decrease medication. He simply didn't need meds, this much meds anymore. That's the important point. So, and this is the patient now after 2 times 2 hours, this treatment. You see that his arms are swinging again. His facial expression, he smiles. And then he went home, was stimulating, was using the glove for 2 hours a day. And this is day 6. So the patient was able to restart working. And the amazing thing is, and that's something we observed in all our patients, that's the amazing thing. In the patient also, the sense of smell and taste came back. We didn't expect this. Parkinson's disease is a multi-systems degeneration. One of the first sites that gets affected by the degeneration is the olfactory bulb. And typically patients have issues, with smell and taste. He was no longer able to cook for his family. After the glove treatment, after 2 weeks, he was able to cook for the family again. And then in November 2018, the patient was running his first marathon. And since then, he did a couple of long-distance races, and tomorrow he's doing his first triathlon, the Floridian triathlon. And you see, that's the important thing. So we started in 2018. It's now 2020. It's a long time. In Parkinson's therapy, there's the typical 5 years window. 5 years it takes until the effects of meds decrease or horrible side effects occur. 5 years. It takes until the effects of DBS disappear. So we are very encouraged because the patient really is in a very stable and perfect condition. And that's not only this particular patient. So the important point based on the results of our pilot studies is, well, first, this treatment helps with respect to all symptoms, also tremor, but it helps, and that's the important point, also with respect to symptoms that do not respond well to medication and also to deep brain stimulation, namely gait issues, as we've seen, balance issues, and also voice issues. And there are other disorders that are perfect candidates, and we'll soon start applying our treatment, and that is essential tremor. All these disorders are characterized by abnormal neuronal synchrony, dystonia, epilepsy, and obsessive compulsive disorder. Thanks for your attention. And last not least, very important, I'd like to thank my great collaborators here, and in particular my fantastic team. Thank you very much.